Hello everybody, how are you? Happy Monday. I guess what we have now is another day to go and work on some more math problems while I realize that my hair is a mess. But that's okay, because we're working on math counts problems and those make us happy. Math counts, as I've mentioned in the previous two streams, is a source of some really creative problems. And what we did in the first two streams of this weekend, this extended weekend, were the questions from the chapter competition, which is the one that goes out roughly to like a city scale. And we were working on something called the sprint round, where we were working on questions that you had to work pretty fast to solve. Now what we're going to do next are questions from the target round. The target round are questions where you typically have 6 minutes to work on a pair of questions. And there are 4 sets of these questions. So I guess if I could do math, that means that it's supposed to take 24 minutes to get through a target round. We have 1 hour today, because what we're going to do is we're going to try to talk through how to solve these questions. And I don't want to just simply do it fast. I want to hopefully teach something as well. Now, something that you will know if you've watched some of these other live streams with MathCounts are that this is an official collaboration with MathCounts, which is what gave us the permission to go and use these problems. Thank you to MathCounts for that official collaboration. But please be aware the questions are copyrighted, so you're not supposed to just go around copying them. The second thing is if you've watched the previous live streams, you will know that I actually haven't looked at the questions before. And that's on purpose. That's because I want to let everyone see how you go about thinking about a question if you've never seen it before. And also you'll see that I occasionally make mistakes. And the goal of the chat is to have everyone help correct those mistakes. All right, is everyone ready? Let's go ahead and start playing with some of these questions. Okay, maintain my streak. What streak? I got a mistake last time. Answer 50 revolutions. That's because we were doing the chapter sprint round. Now let's move on to the target round. The target round also, by the way, allows you to use calculators. And I already see that this question has a lot of digits. If there are 0.624782 lugs in a peak, then how many peaks are there in 200 lugs? Express your answer to the nearest integer. Well, first I'm going to tell you what I'm going to do. I've got 2 numbers. What are you going to do with these 2 numbers? Add, subtract, multiply, or divide? Well, I think we'll have to do some kind of dividing. Because if I want to know how many peaks are in 200 lugs, how to scale this? Sometimes I often think of it by drawing some kind of thing which is like 0.624782 lugs is equal to 1 peak. And what I want to know next is how many is 200 lugs. And I know this is, like, there are lots of different ways that people go about doing this. Some of them use fractions and multiply them. I'll show you one way I often think of it. I think, well, if that was true, that's an equation, right? And so what I want to do is I want to know how to transform one equation into the other one. And I'll do that by multiplying both equations by the same thing. If I want to turn that into 200, then what I need to do is multiply by 200 divided by that, 0.624782. And so that's how I would go from here to there. Oh, I know how to multiply 1 by that number. It's just that number. So 200 lugs is 200 divided by 0.624782. Yikes. Is this fun? Okay. I'm going to be silly. Okay, first of all, I'm going to tell you something. It's that this does let you use calculators, and I'm going to go and pull up my calculator in a second. But I'm going to tell you what I would do if I didn't have a calculator. And the answer would probably be wrong because I will not be the nearest integer. But if I actually had this problem in real life, you know what I would do? I would say, here's a really nifty fact. Does anyone know that 0.625 has a really nice fractional form? 0.625 is a really, really nice number. 625. That's 25 squared. That's nice. But it actually is, as I see in the chat, a bunch of people know that this is 5/8. And that's because 1/8 is 0.125. 4/8 is half. You know, like if you think about it, it does make sense. 5/8 is 0.125 plus 0.5. That's 0.625. So I'm going to be like kind of silly here and say, yeah, I know you're supposed to use a calculator, but I'm just going to first of all say, just for my own satisfaction, if I had to do this and get a rough approximation, which will not really be right because 200 is too big of a number, if I really had to do it myself without a calculator, I'd say that this is equal to 200 times 8 over 5, 5 into 200, and it's going to be wrong, but I still want to do it anyway. This is 40, I think, if I could do that. And so I would be getting something like 320. But I'm doing this so I know approximately what the answer should be. Now let's go pull out our trusty calculator. I don't have a calculator, so I'll just use my 4-function calculator on my phone. And so I'm going to go and start like doing this random division. And I want to tell you, the reason I did the approximation is if I get an answer that is far away from this, then I'll say, maybe I typed something wrong. All right, I'm really slow with calculators, which is why I generally like not using them. 200 divided by, what is this? 0.624782. What? 320.1. Hey, it's good. Yeah, okay, I don't know why I'm holding this up. All right, yeah, this is amazing. 320.1. Okay, this was actually pretty good. So the answer is 320, I think. We didn't check the answer yet. But before I go and check the answer, I'm going to tell you, I actually had a decent shot at it. Because look at that, 0.625, kind of close, you know? But I wouldn't know for sure until I actually typed it in. It's always good to have these both, like one thing where you know roughly what it should be, and then just like type it in, because it's super easy to type something in wrong. All right, what's the real answer? Let's see. Yes, it was right. Next question. Consecutive integers are arranged in 3 columns in the pattern shown. What number will appear in column C in row 22? 1, 2, 3. At first I was like, what? Aren't there just like multiples of 3? But no, it's not. Because it's like 3 is here, then it's 6, then it's 9, then it's 12, and then it's 15. Oh, I see. So it's the odd rows that are going to be the multiple of 3. I can do that. So I just need to know row 21. We can do this. We totally can do this. Row 1. Oh, I noticed about odd and even rows because odd rows goes this way, even rows go that way. So that means row 21 is going to have 3 times 21, right? Because that's 3 times 3. That's 3 times 5. So all the way down to here, let's go to row 21. So I'm going to get row 21, and there will be an A, and a B, and a C. All right? And the C in the row 21 is going to be 21 times 3. I can do that without a calculator. That's 63. And in that case, if I want to know what's right under it, 64. I think the answer is 64. Oh, I see that somebody in the chat has asked, you want row 22, not row 21. That's right. I went to row 21 because it's like it goes across to there, and then you go +1 as you go down. That's why I did row 21. Because if I'm looking at the even rows, unfortunately the even rows don't have 3 times it over there. They have 3 times it in the A column. Okay, what's the answer? Let's find out. Yay, it's 64. Okay, next question. Jamie makes 120 slices of toast and puts at most one spread, jam, butter, or avocado, on each slice. She puts jam on 1/3 of the slices, butter on 15 of the slices, and avocado on 50% of the slices. How many slices of Jamie's toast have no spread? Okay, so I just need to go and figure out what's going on with these 120 slices of toast, and it's either jam, butter, avocado, or just toast. Okay, jam, 1/3 of the slices. So, jam, 1/3 of the slices is 40 slices. Next, I have butter. Guess butter is yellow. Butter, 15 of the slices. Oh, I don't have to do anything. And the last one is avocado. Oh, I shouldn't have used green for that. Oh well, avocado. This is a really bad avocado. It's like pink. Don't eat pink avocados. 50% of them. 50% of 120. That's equal to 60, I think. Okay, so now what do I have? I have 40, 15, and 60, and I need to know what's left. Ah, that's not that bad, because that's 55, that's 60, and 60 times 2 is 120. So if I look at this, I actually can see already. That's 55, which is 60 minus 5. That's how my brain works. This is 60 minus 5. And over here is a 60. And all together is 120. So that means that what's missing is 5, right? Because the 60 plus 60 gives me 120 already. So the plain stuff is just 120 minus 60 minus the 60 minus 5, which is actually just 5. I think that's the answer. Let's find out. Yes, it is. Question 4. Segment AB is 2808 units long. Oh, I know where this is coming from. Okay, whenever I look at a problem, I'm like, where are those numbers coming from? What kind of a crazy number is 2808? Is it like I know it has a nice prime factorization? But it's an awful lot like 1404. And my brain is thinking about the square root of 2. And the square root of 2 is 1.404. Okay, let's keep reading the question. I just saw something related to square root of 2. Point X is the midpoint of segment AB. Point R is 3/4 of the way from X to B. Point S is 5/9 of the way from X to R. How many units long is segment RS? Wait, I don't even need to use the fact that it's the square root of 2. Oh well, that was just fun, but it's not necessary. It really felt like it was going to be some square root of 2 somewhere. But let's just go and draw something now. So, okay, draw a number line. Not a number line. Draw a segment. AB. Nice long segment. That wasn't straight enough. Maybe a bit better. A, B. 2808 long. Point X is the midpoint. Oh, I know what that is. That's the middle. X. Always draw a nice picture. Okay. Next, point R is 3/4 of the way from X to B. Okay. Let's go and cut that. 3/4. 3/4 of the way from X to B is R. Next, point S is 5/9 of the way from X to R. 5/9. Oh, how cute. It's already in thirds. I like that. If it's already in thirds, then it's like I can cut those into ninths even easier. I'm just drawing a scale drawing for fun so that we can look at it. 5/9. This is S. Okay. And the question is, how long is RS? Okay. So let's do this by fractions, right? So the way I often look at this is I say, well, what fraction of the whole is the SR? Let's write down a few things. SR. I don't know what fraction of the whole it is, but I can tell you what fraction of XR it is. SR is 4/9 of XR. And the reason is because, well, you can see there's 4 out of 9, but it's also because this guy was 5/9, so this is 4/9. So SR is 4/9 of XR. Okay, what's XR? I'll write it as, this is 4/9 of, well, XR as a fraction of B, that's 2/3. Not of B, of XB. 2/3 of XB. Wait, what just happened? No, it's not. That's not 2/3. That's 3/4. I'm reading the question again to be careful. So that's 3/4. So I'm looking at it because it's like, what do I know about r? Point r is 3/4 of the way from x to b, so xr is 3/4 of xb. And what's xb compared to ab? Half of it. All right? So this is 4/9 times, the 4 looks too much like a 9. This is 4/9. You can see I cared about the handwriting because I've made mistakes on math contests before where I write something and later I look at it and I misread it. So I'm afraid of 4s and 9s looking the same. So what do we have here? Okay. So 4/9 times 3/4 times 1/2 of AB. Well, I'll just write down what AB is. 2808. Okay? So if I have all of this, I just need to go and figure out what's that big multiplication. As the lazy person, I'm going to go and not use the calculator if I can avoid it. So the 4 cancels the 4. The 3 and the 9 gives me a 3 here. And now I just need to divide 2808 by 6. All right? And I know you get to use a calculator, but I'm going to do it anyway. And the reason I know it's going to divide nicely is I just used a divisibility trick in my head. That's a multiple of 6 because it's even. And also it's a multiple of 3. I know it's a multiple of 3 because 8 plus 8 is 16. Plus a 2 is 18. That's divisible by 3. So this will divide nicely. Okay? So in that case, I get 6 into this. 6 times 4 is 24. 48. Ooh. 6 times 8 is 48. So in that case, my answer for the SR appears to be 48. That wasn't the fraction, so that makes me happy. But let me double check. Whenever I do these kinds of questions, I want to go and see whether or not there's a mistake. So we always want to go and make a check, right? So the segment A is 2808 long. I always look at these things. X is in the middle. R is 3/4 of the way from X to B. Yeah, that's what I drew. S is 5/9 of the way from X to R. Okay, we're checking our answers. And this is what you should do on math counts. You should always check your answers. All right? So now how many units long is this? All right, so now I know that this guy is 4/9 of that. That's what that made sense. That is 3/4 of this piece. Okay, and then this piece is 1/2 of the whole thing because X is the midpoint, AB is the 2808. So I have this thing here, and I have, yes, and I'm good. And then so I have to do this cancellation, and as we're checking all of this, the 4, 4, 4, 2808, and all I have to do is divide 2808 by 6. Wait, what's this? What happened to the O? Oops, this is why checking is useful. So whenever you're doing a problem, make sure you check it carefully. What is going on here? 288, I'll tell you why I wrote 288. 288 is a really nice number. 288 happens to be like 144 times 2. So in that case, what we need to do, and that's like the nice number that we're used to seeing around. And it makes me just want to write it down. But what happened here? Okay, let's put the O. So it has to be 40. 6 times 6 is 36. And now it comes out 48. 6 times 8 is 48. Good. So now I have 468. And this is also making me realize I should have done a double check. Does it look right that that's 468 if the whole thing is 2808? Yes, because it's like, it's small, but not that small. I mean, the 48 would just be ridiculously small compared to 2808. So let's try this. Is the answer 468? And by the way, this is also how you should be doing it on math counts. If you have any time left, you should go back through and like check, sanity check the various things you've done. And occasionally you'll notice something like this. Okay, what happens? Yes, it is. Let's continue. Ooh. Question number 5, toothpicks. 20 toothpicks, each 6 centimeters long, form a figure consisting of 6 equilateral triangles and a rectangle as shown. What is the total area of the figure? Express your answer as a decimal to the nearest hundredth. All right, let's do the easy parts first. So there's this big old rectangle in the middle. If it's 6 centimeters long, that's 6, and that's 18. So the inside is going to be 6 times 18. I think that's 108, if I remember correctly. I'll tell you how I just did that. 6 times 18 is 6 times 6 times 3. That's 36 times 3. I see that number a lot. And you can almost like multiply that. That's like 108. 108 just appears a lot in these math things. So this is 108. The inside here is 108. Now I need to worry about all of these little guys. So each of these is 6 centimeters long. That means I have an equilateral triangle. I have 6 of them, actually. Wait, is that right? 1, 2, 3, 4, 5, 6. Yeah, I've got 6 of them. So next thing I need to do is I need to know how would I go and make the area if it's 6, 6, and 6. Well, the area of a triangle is half base times height. And in an equilateral triangle, it's really nice. If that's 6, this is 3, and this is 3, and that's 6. Now, this kind of a picture is a 30, 60, 90 triangle, which is very, very common. And I saw somebody in the chat actually posted there's a formula for these, and you can use the formula. But I actually always just write it because I find it easier to see it. There's an equilateral triangle here. You can use the Pythagorean theorem to figure out this height. But the way I often think of it is I say, you know, if I wanted to get that kind of a picture, that's like 3 times of this kind of a picture. 2, 1. Now that is very easy to Pythagorean theorem. If I want to know what's over here, the Pythagorean theorem just tells you, you know, that's the square root of a squared plus b squared, right? How many people think that this is what you should do? You know, if I have 2 sides, the Pythagorean theorem is the square root of one of them squared plus the other squared. Well, you know, I said that on purpose. That's actually wrong. This is a common mistake. A very common mistake is you get super excited when you're using the Pythagorean theorem and you just bam. But the problem is that's the hypotenuse. Since that's the hypotenuse, you better put a minus sign in between. And the reason you put a minus sign is so that 1 squared plus that thing squared is just the 2 squared. Perfect. I did that on purpose, by the way, just to let you know. I did that on purpose because I've made that mistake before, and I just wanted to emphasize, be careful on every Pythagorean theorem not to go backwards. But the square root of 4 minus 1 is the square root of 3. So now, whenever you have these, it's like a 2, 1, root 3 type pattern. That means it's 2 times 3, 2 times 3, 1 times 3, and root 3 times 3. So that height is 3 root 3. And that's the formula I think that some people were posting in the chat. Half base times height. Well, here's half the base. It's 3. Times the height is 3 root 3. 9 root 3 is the area of that triangle. Somehow whenever I do these equilateral triangles, I don't even do like 1/2 times 6. I'm just like, it got cut in half. My brain just says, that's half base. It's 3. 3 times 3 root 3, and that's it. Oh, and if you want to know why, it's also cool. If you cut this, if I could cut my screen, and if you took this guy and flipped it over and put it over there, you'd actually get a rectangle. You'd get a rectangle which is 3 by 3 root 3, which is why it's 3 times 3 root 3, 9 root 3. Okay, so now we know that each of these things is 9 root 3. Next thing we do is that 9 root 3 multiplies by 6, and if you multiply 9 by 6, that's 54, right? So this is 54 root 3. And so the answer is going to be 108 plus 9 times 6, 54 root 3. At this point, we're going to have to pull out our calculator. But before we do this, let me go and just double check and make sure that we didn't make a mistake, because I seem to have a little bit of time to do so. The way I would do this is I would say, okay, wait, this is 6, this is 6. This is 6 times 3 is 18. Okay, if I multiply those two, I actually know that's going to work out. That's 108. And now I've got 6 of these guys. And actually, I do sort of remember a formula. The formula was you sort of square half of the side length. And that actually matches what we did here. Okay, now we calculator it. Oh no. Does my calculator even have a square root sign? Make sure you use a calculator that has a square root sign. I guess if I turn it this way, sometimes the phone calculator gives me square root. Oh, it does. That's awesome. All right, let's do this now. So I want 108 plus, what is this? 54 times the square root of 3. Okay, and my answer that my calculator spat out is 201.53. Now I'm going to do a sanity check. Do I believe that? Well, I'm going to look at the picture, and I'm going to say, could I believe that the answer is 201.53? Well, that's what 108 looks like. It looks like that. What would it look like if I put 6 triangles? Watch, I'll make 6 triangles. If I just like did this, oh, I'll do it at the bottom. This is what 6 triangles looks like. This is how I sanity check my work. How many people agree? Like I had to take 6 triangles. 1, 2, 3, 4, 5, 6. If I just shove them all onto the bottom, that's what that would look like. So in that case, if that's the case, then I just need to know, does it make sense that if that's 108, that thing would be around 100-ish? Looks like it. It's okay, because otherwise I am always afraid when I type something in the calculator. I'm afraid that like I put my parentheses wrong, or I don't close the square root, and if you get an answer that's just totally nuts, you wouldn't know. But if I look at this, I'm like, yeah, I can believe that. It's probably 201.53. Let's see if that's right. It is. Okay, let's go to the last 2 questions of the target round. And we're good. We still have time to continue talking about these today, because the live stream is scheduled to run until 7:30, and we should be able to finish the last 2 questions by then. All right. There are 10 coins on a table, head side up. Noah wants them all to be tail side up, but with each move, he must turn over exactly 6 coins. What is the fewest moves he can take so he ends up with all the coins tail side up? Okay. So now what's going on is that I can turn over 6 coins at a time, but it's really annoying. If I could turn over 5, that would be great, because then I would just do it 5 and do 5 more. But with 6, you kind of overdo some of them. This is a really nifty question. Okay. So let's just try. Let's see what happens, okay? So if I had these 10 coins, the way I would think of this is I would first say, let's try some greedy algorithm, okay? There might be more clever ways, and we might get a proof soon. But let's start with a greedy algorithm. If I want to turn them all up somehow, I can flip over 6 of the coins. So if I start with 10 heads, 0 tails, I can do 1 motion, and I can get 6 of them flipped. So it's now 4 heads, 6 tails. All right? Next, suppose I'm greedy. Let's go and fix all of those heads. So flip all 4 of them, but also flip 2 of those. What would happen? Oh, this is cool. Okay. I'm going to do something else right now. I'm going to adjust this, okay? I already see an interesting idea. I'm going to write ordered pairs. 10. Oh, I have something even better. I'm going to write just the number of how many heads there are. 10 heads. Okay? From 10 heads, I'm able to turn 10 heads into 4 heads. 4 heads. Anyway. This is possible. Okay? And I'm not telling you how many tails there are, because it's like, well, there's 10 coins, right? And if there's 10 coins, then the number of tails is 6. What I'm doing here is I'm writing the minimal amount of information, okay? So if I write 10 heads, that tells me everything about my situation, and the only thing I can do from 10 heads is to make 4 heads out of it. Next, suppose I have 4 heads. What could I do? Let's draw a little picture to let us see how this is. And I'm actually showing you how you do this whole thing out if you wanted to make sure you didn't make a mistake. So this is 4 heads and 6 tails. Okay. If I want to know what kinds of things I can make, well, one thing I can make is I could grab all 4 of the heads and flip those, and also flip 2 of the tails. That's a legitimate thing that you could do. If you did that, what you'd end up getting is you'd flip all of those into tails. You'd get 2 of the heads, and the rest would stay at tails. So what I'll say is that this thing is capable of turning into 2 heads. But what else is it capable of doing? Let's be careful. So this is capable of turning into 2 heads. But it's also capable of, if I don't grab all of the heads, what if I grab only 3 of the heads? It does that. Now, I'll have 1 head here. Those become heads. Those 3 tails become heads. And these heads become tails. And those tails stay tails. All right? I'm trying to be careful and make sure I looked at all the possibilities. Just reading the question to make sure I understand. Turn over exactly 6. Good. What have I achieved? Nothing. I'm able to do nothing if I want. I could turn 4 heads into 4 heads. All right? What else could I do? Another possibility is what you flip over is these 2 of the heads and 4 of the tails. Now I will get a heads and a heads. I'll get these heads. Oh, cool. And I'll get these tails, and these are tails. It looks like I can make 6 heads out of this. Let's call it 6 heads. And I can go here. But actually, there's more I can do. If I went and just picked 1 of the heads, what else could I do? If I picked 1 of the heads and 5 of the tails, I could make heads, 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 heads. That's 5 and 3. Okay, it looks like 8. I can make 8 heads as well. So here are all possible things that I can do. And by the way, if I just grab the last 6, I can just turn them all back into heads. And what I'm realizing now is I shouldn't even write arrows. This is what's called a graph, actually. What I've just drawn here has a name. In fact, the area of math I specialize in is graph theory. What I just drew here is a graph which is saying from all of these different positions, here's what I'm able to do to move to another position. And I can move in either direction along this, right? I can move in either direction along one of these lines. So I can go from 10 to 4 to 2. I can go from 10 to 4 to 4 to 4 to 4 to 8 or something. But I already see, if I want to get to 0 heads, I can get there from the 6. So in that case, I know the 6 goes to 0. So I already know that there is a pathway. I already know there's a pathway that has only 3 of them. 1, 2, 3. And I know I can't do any better because from the 10, I can only go there. From there, here are the only places I could go. And one of them lets me get to the end. So I'm done, right? And this is actually how you do these kinds of questions carefully, because there's not actually a clear system immediately to me. On the other hand, if you can see what you're able to go from and to, then you can see, yes, there's no way I could do it any shorter because I've already explored everything I could do in 2 steps. So I'm going to say that the answer is 3. Okay? So I see that some people have some questions about, like, is there anything else? Wait, you can turn a coin twice. Yeah, you probably have to turn a coin twice or else you wouldn't be able to even get there. Actually, let's see if that's the answer first. Is the answer 3? Yes, it's 3. And in general, when every of these games, they're quite hard to analyze. That's actually why people have to write computer programs usually to analyze games. We have 29 minutes to attempt to solve the last 2 questions. Obviously, I couldn't count. So we still have 2 more questions to go. No wonder, that was hard. That was harder. Yeah, that was a harder question. It took us a while to go. Okay, let's keep going. Suppose that n is a positive integer for which the product 35n is divisible by 60. What is the least possible value of n? Okay, when I look at this, I think about canceling, actually. I think about prime factorizing and canceling. I need to be able to cancel out a 35. Prime factorize. 35, no, not 3. It's not, 35 is not 3 times 5. It's 5 times 7 times n. I need it to be able to be divisible by 60. 60 is 5 times 12. I'm actually going to just write that there. Look, what kind of canceling could I do? Well, if I could let n be 0, I'd be really happy, but n has to be a positive integer. And if you see what kind of canceling is going on, I was happy to leave the whole 12 because you're not going to get any 7s. I'm not going to be able to cancel the 7. So the best I can cancel is the 5 against the 5. And so I better be able to cancel the 12. What's the best way to cancel a 12? With 12! You have to be able to eat up the whole 12. And the 7's not going to help you at all. So I'm going to get the answer of 12. Okay, let's see if it's right. It is. And that leaves us 27 minutes to do the last question. The grand finale of the individual round on math counts. In math counts, the sprint and the target are the 2 main rounds for individual score. And so this is like the grand finale. Let's see what this is. Hardest question on the whole batch. Tim has a collection of square tiles of various sizes, each of which has an etched quarter circle with radius equal to the side length of the tile. Tim arranges 8 tiles as shown. If the 2 smallest tiles each have side length 10 centimeters, what is the length of the resulting spiral formed by the tile's etchings? Express your answer in terms of pi. This is a Fibonacci spiral. I like this. That's actually what it's called. A Fibonacci spiral. You'll see why soon. Okay. Now, here's what I'm going to do. 10. Too big. Too big. I don't like 10. I want 1. Okay? I'm going to do everything where I'm going to write 1, and 1 is going to mean 10 centimeters. Actually, since this is metric, we also have a word for it. Does anyone know what 10 centimeters is if I want a 1 thing? 10 centimeters is equal to 1. It's called a decimeter. DM. Decimeter. That's not really important, but I'm just going to write 1, okay? That'll make my life easier. So, oh, someone says there's a buzzing. I'm sorry if there's a buzzing. I hope there wasn't one. But let's keep going. Now those like the smallest tiles have side length of 1. Okay, so they're 1 now. 1. And 1. Really small ones. Oh, what's 1 plus 1? 1 plus 1 is 2. If that's 2, then this part is 2. I'm not writing the spiral length. I'm writing the side lengths, okay? So you see, that's 2. If that's 2, there's a square here. So if that side is 2, that side's also 2. Oh, did we say that this was 1? This is 1. If that's 1 and that's 2, then that whole length is 3, which is over here. Oh, that's part of a square. If that side is 3, that part's also 3. Ah, 2, 3. If that's 2 and 3, then this whole thing is 5. Does anyone see why I called this a Fibonacci spiral? That was supposed to say 5. That's 5. So that means that's also 5. Well, in that case, 3 plus 5 is 8. So that means that this side is 8. Okay, if that's 8, then this thing here is also 8. That's like the side length, not the curvy part. So now 5 plus 8 is 13. 13 up there. $13 over here. 8 plus 13 is 21. Okay, and now I've worked out all of the different lengths. So now what I need to do is I need to know what happens to all of these lengths of the curves. So now the important thing is that if you look at what's going on, everything scales. Actually, compare this particular curvy thing to that curvy thing. They're the same, nothing special. But how is the curvy thing here compared to the curvy thing with the 2? Well, the curvy thing with the 1 on each side compared to the curvy thing with 2 on each side, the length of the curve should double. Does that make sense? Because it's like I took this little guy and I blew it up by a factor of 2. So whatever that length is, that'll be twice the length. So now here's what I'm going to do. I'm going to say that little tiny length in there, I'm going to call it L. And we'll worry about what it is later. So if I had this, well, let's not use white because white is used elsewhere. If I have this 1, remember it's a decimeter, by 1 decimeter, we have this thing here that was supposed to be a quarter circle, and let's call that L. Maybe let's draw an arrow. L. That's L. Okay, so if that's L, let's go figure out the whole thing in terms of L. I've got 1 L, another L, 2 L's, 3 L's, 5 L's, 8 L's, 13 L's, and 21 L's. That's what I've got. I've got to write all this Fibonacci nonsense. So what I've got is the entire thing, the big old spiral, is going to be, can I fit it here? Let's try. It's 1L plus 1L plus 2L plus 3L plus 5L plus 8L plus 13L plus 21L. Yikes! Does anyone actually want to add that much stuff? That looks painful. But that's okay. There's a shortcut. Let's factor out all the L first. whatever the L is, I need to know L times 1 plus 1 plus 2 plus 3 plus 5 plus 8 plus 13 plus 21. So my answer is L times 1 plus 1 plus 2 plus 3 plus 5 plus my head plus 8 plus 13 plus 21. Okay? I need that. Now you gotta say, somebody should have figured out how to add Fibonacci numbers. Maybe there's a pattern. Let's go and figure out what this is. Okay? So now let's go and try to add up all of these these Fibonacci numbers. Could there be a pattern? Well, let's try. Let's just suppose I have the Fibonacci number. And let's also write the sum. We're going to make a table. Okay? That was supposed to be horizontal. Fibonacci number and the sum I've gotten so far. Big old table. So we start with a 1. The sum is just 1. It's like 1. All right? The next one is another 1. And the 1 plus 1 is a 2. The next Fibonacci number is a 2. And 1 plus 2 is 3. The next Fibonacci number is 3. 1, 1, 2, 3. And, the sum so far, 1 plus 1 plus 2 plus 3, what is that? 2 plus 2 is 4. 4 plus 3. Wait, is that what I wanted? No, I can't add. What's this 3 doing here? That's not a 3. Bye-bye. Okay, so no, that's not a 3 at all. 1 plus 2, last time I checked, is 4. Okay. 1 plus 1 plus 2. Wait, can I add? Something is fishy. Let me go back here. 1, 1, 2, 3, 5. That's what I wanted. 1 is 1. 1 plus 1 is 2. Okay, is 4. And then the next one is 7. Oh, this is good. All right, because 1, 1, and 2 is 4 plus 3 is 7. And I'm telling you how I'm checking it. The way I'm checking it is I'm also saying, there's another way to get this 7. If I knew that the sum so far is a 4 and I add a 3, then I just go 3 plus 4, 7. Bam. Okay, let's keep going. The next one, 1, 1, 2, 3, 5. And let's use that now. I know that the sum all the way up to here was 7. Add a 5 gives me a 12. Next is 1, 1, 2, 3, 5, 8. 12 plus 8 is 20. And the next thing is 13. 13 plus 20 is 33. And then the next thing is the 21. Just a second. 8, 13, 21. And if the sum of all of these was 33, adding a 21 gives me, what is this? 54. Okay. That's what I wanted. 1 up to 21. But I did this on purpose. Does anyone see a really nifty pattern that can help you save a lot of time next time? There is something incredible about this. It's an amazing pattern. Oh, people are talking about hearing planes and helicopters. Yes, there are helicopters that fly overhead because this is near a hospital. And so their helicopters are always landing at the hospital. But there's something going on here, which is that, look at the pattern. These are the sums of Fibonacci's. Does anyone see anything kind of neat about this column? What's special that you can use the next time you ever have to do this? If you add up Fibonacci numbers starting from the very first one, 1 plus 1 plus 2 plus 3 and so on, these aren't like totally random numbers. The number plus the next number minus 1 is the sum. So what's going on is these are actually pretty close to Fibonacci numbers. How do I turn these into Fibonacci numbers? Come on, what's this? 1, 2, 4, 7, 12, 20, 33, 54. What kind of a crazy sequence is that? Well, it's pretty close. You know what you can do to every one of these numbers to get a Fibonacci number? Take this whole column, and for every number, just add 1. 1 plus 1 is 2. That's a Fibonacci. 2 plus 1 is 3. Whoa, that's a Fibonacci. 4 plus 1 is 5. That's a Fibonacci. 7 plus 1 is 8. That's a Fibonacci. 12 plus 1 is 13. This is cool. 20 plus 1 is 21. 33 plus 1 is 34. That's the next guy. 54 plus 1 is 55. That's the next one. It's awesome. Fibonacci's are so full of these kinds of patterns. And so actually what's going on is that whenever you take a bunch of Fibonacci starting from the beginning, the answer is always a Fibonacci minus 1. Is 54 a Fibonacci? It totally is. Let's write this down. So the next one is 34. And after 34 is 55. So 55 is totally a Fibonacci, right? So actually what's going on in this whole sum here, you're always getting another number minus 1. And that's actually how you can also check your answer. If you're doing all of this and you know you're doing this and you're like, oh, okay, it is the next Fibonacci minus 1. That's what's going on here. Okay? And people are observing that it's sort of like how infinite geometric series add up to a whole number or something nice because it gets so small. There's this another really cool fact. I don't know how many of you have noticed this, but 1 plus 2 plus 4 plus 8 plus 16 plus 32, add up a bunch of powers of 2 starting from 1. You know what you always get? You always get the next power of 2 minus 1. And with Fibonacci's, what you actually get, if you add up all the way up to here, is you get the next Fibonacci minus 1. And the actual reason, if you ever wanted to prove why this is true, it is because the way we're getting these is, all right, here's why it's true. Look how I get the next number. To get the next number, what am I really doing? I'm taking 34 plus 54. But 54 is 55 minus 1. So this number here is going to be 34 plus 55 and then minus 1. You know what's 34 plus 55? That guy. So the reason why this number is always the next Fibonacci minus 1 is because to get this number, I take that thing plus the new one, plus the 34. And that thing from what we know before is going to be that one minus 1. That's the principle of mathematical induction, which I even talked about in this live stream. So actually, if I want to know what to write here, I can get that by just adding those two and subtracting 1. I know what the sum of those two is. Next Fibonacci, and then minus 1. That's why it works. Okay, let's finish the problem now. 54, that's what I wanted. And I'm showing you these tricks so that as you're doing this work, it's like if you added it all up and you got some weirdo number, and it's not a Fibonacci minus 1, then you know you made a mistake. 54L. That's what I want. I want 54L. What's L? That thing. Okay, now let's go and figure out what that thing is, and we need to figure out the length in centimeters. Okay? What's L? L. Well, now we actually go and write this down. So I've got L, which is the curvy part. And what I've gotten here is 10 centimeters. We're now going to be careful. Okay, so L is going to be a quarter of a circle. So L is equal to a quarter. And what is the formula for the circumference of a circle? 2 pi r, right? So 2 times pi times the radius, which is 10 centimeters. Now everything's in centimeters. Okay, time to go and cancel. The 4 and the 2 and the 10, well, we can cancel that. That's not bad. This goes to a 2. You know what I'm going to do? I love 10. I love multiplying by 10. And what I care about is 54L, right? That's what my answer is going to be. My answer was equal to 54L. Where'd my 4 go? 54L. But I love the 10. I want to keep the 10. So look at what L is. L is equal to pi times 10 divided by 2. All right? So I'm going to call it 10 pi divided by 2. And that's like not simplest form, okay? You wouldn't use that as your final answer. But why do I like that? It's because I can take the divide by 2 and whack it against the 54. So this is equal to 54 times 10 pi divided by 2. I would much rather divide the 54 by 2 and then times 10, right? Because as you know, I'm too lazy to pull out my calculator. To do that, I need to unlock my screen, and that just takes too long. Divide this out. Okay, what is this? 2 times 2 is 4, and then there's a 14, so 27. Okay, so I get 270 pi. Okay, so I think that's the answer. Let's do a final check. All right, let's go back and see what we've got. What was this question again? Make sure we understand it. Got all these tiles, got all these quarter circles, okay, and there are 8 tiles as shown. Oh, neat. When I see that number 8, I want to go and make sure I did enough of them. So then I go here and I'm like, do I have 8 of these that get me to the 54? 1, 2, 3, 4, 5, 6, 7, 8. That's good. I'm always afraid of being off by 1. Okay, 8 squares, 8 tiles. The two smallest ones are side length 10 centimeters, which we called 1 just to make our life easier. And then now this is the Fibonacci spiral. It will be 1, 1, 2, 3, 5, 8, 13, 21. And it's because of this beautiful pattern that I just keep adding the previous one and the next one. Okay, that works. So now I've got this. Oh, and another reason why you should be happy to see Fibonacci's is because maybe your math teacher told you at some point that Fibonacci's appear everywhere in nature, like with pine cones, snail shells, and everything. So if you get Fibonacci's out of this, you should say, thank you to my math teacher. She or he showed us that thing, so I'm now happy that I saw there's a Fibonacci here, because that means I'm probably on the right track. Okay. And then now what we have from here is we need to add up all these Fibonacci's. We saw this super cool pattern. That is the next Fibonacci, the next Fibonacci minus 1. Great, 54 is 1 less than a Fibonacci. So now I need 54 times this guy, 10, 2 pi r. Yep, that's good. I want a quarter of the circle. I kept the 2. Half, that's 54. Yeah, I think this is good. 270 pi. The moment of truth. Let's see if this is right. It is! And that finishes our target round. Okay, well then, that was the math counts. It was pretty fun. We even got to see this snail shell at the end. We've got like 11 minutes left, or 10 minutes or something. So what I usually do if we've got some extra time at the end is I'm happy to answer random questions about, about math counts or other things. Unfortunately, I don't have time on this one to just teach a particular math lesson. Those of you who remember, I actually used to do those are like hour-long streams where we just teach random math lessons based on what people are asking. But from my experience there, you can't do that in like 10 minutes. So I'm happy to take like general questions. So let's go right away. So Lee Random has asked, do you think chapter invitational will also be this easy, or will it be harder? Now, I don't know. I'm not the one who writes these problems. But I will tell you, in every previous year of math counts, the chapter is easier than the state, and the state is easier than national. This I know is true. I've never seen a chapter invitational before, but if they're following that trend, quite possibly it will be. And I will also say, I know that the chapter to the state usually jumps up quite a lot in difficulty. Some person has asked me, what is a good green screen? The answer is, as long as it's green. Okay, more questions. Somebody asked me, am I a teacher anywhere? Because I might be a good math teacher. So first of all, you're lucky you've got a real math teacher in your school. So please make sure to go to their lessons. I am a teacher somewhere. I teach at a university, Carnegie Mellon University in the United States, Pittsburgh, Pennsylvania. I actually do stream my classes, and they are online every Monday, Wednesday, and Friday, 2:10 p.m. But they're university level, so they're actually probably quite a bit too hard for most of this audience. That said, if you want to watch, you're welcome to watch. Okay. Great. I mean, I'm doing this because I'm actually a Math Counts alumnus. I didn't mention this in today's stream, so I'll make sure to say it now. Math Counts to me is one of the source of the interesting questions that got me really interested in math when I was in middle school. So when I had this opportunity to officially work together with Math Counts to run this, I said, you bet, I'm definitely going to do this. But the normal math that I teach is usually like college level stuff, which is why whenever I start talking about something, you'll see I kind of go off on these proofs, and I want to show you like why things are true. Because at the university level, like all of our problems are about explaining why things are true, as opposed to getting a particular answer. More questions. Whoa, chess and lattes. What's the best way to win math counts? Well, here's the advice I'd give you. I didn't play math counts to try to win it. It's not really a good bet to say you want to just do it to win it. I did math counts because I wanted to beat the problems. So let me give you strategies on how to beat the problems. The way to do that is to do kind of what you just saw us doing. We were playing with them. We were messing around. We were checking our answers. We were thinking of many ways to do questions. We were being as lazy as possible to not pick up the calculator. This is how to learn how to beat problems. And if you just do this, you'll get pretty good. Will you win math counts? Actually, probably not. It's really hard to win math counts. But that doesn't matter. That we were doing this not to win. We're doing this to go and learn something interesting. Okay, more questions. Oh, Ethan asked, will I be going over the AMC 10 and 12? Actually, I wasn't planning to. I actually don't usually spend all my day doing these kinds of things. So it's just because of math counts and because of what it means to me and the fact that we had this this relationship that I was like, let's definitely go and do this thing. But the good news is there are a lot of other people in the world who are doing live streams or discussions of AMC 10 and 12. And I strongly recommend, there are lots of other good teachers out there. You can go and find other people's. Ooh, somebody asked, are you a coach at MathCounts? Why, actually, yes, I am, under normal circumstances. So my kids actually also go to a school. My daughter is now in high school. But for many years, I would coach the local MathCounts team at my kids' school. So I would just go in every Sunday and do this kind of thing, live solving questions. I love doing that. But unfortunately, it's not safe for me to do that right now because actually we're generally trying to keep some distance. So that's just why I'm doing this with everyone here instead online. More questions. Somebody asked, do you know if mass point geometry is helpful in MathCounts? The answer is it can be, but you don't really need to use the super high-powered techniques. Usually MathCounts tries to do everything in a way where you don't need like super crazy theorems in order to solve every question. What is this question? Somebody asked, Lee Random asked, how tall are you? Well, it really depends. It depends on what I'm showing. Like I can be really short. I can also be bigger, maybe taller. But ultimately, if you want to know in real life, okay, it's like what? I think I'm like 5 feet 6 inches. I think that's what it says on my driver's license. Something like that. Okay, let's keep going. Somebody asked, chess or checkers? I guess I sort of prefer chess, but I like these like crazy variants of chess where you sometimes have like 2 people against 2 people, and when you take a piece, you give the piece you just took to your partner, and then your partner in one of their moves is allowed to just like put the piece down almost anywhere. And by doing so, you can be like really aggressive when you play chess. People here know what this is called. This is called bug house. I've never actually played bug house checkers. Is that possible? Probably not. That'd be really messy. But anyway, so this is why I like that particular variant. Okay, more questions. Oh, neat. Jason's son. How much math do you need to know to work at NASA? Actually, NASA and rocket science and engineering in general require a huge amount of math. When I say require, I shouldn't say like, it's like you'll be terrible if you don't have it. But if you do have it, you'll be powerful. And I think this week is actually E-Week. I think I saw MathCounts sharing on their social media something about, I think, Engineering Week or celebrating engineering as a profession. And actually, having a really strong math background helps you a ton. And the reason is because whenever you're making something, it's nice to be able to have some sense of what's going to happen before you make it. Like what makes engineering so special? It's that people can make things and they work. But you don't do it by being like, hey everyone, let's go and build this big old rocket and then just like press go and see what happens. And if it doesn't blow up, we succeeded. No, if you want to do this thing properly, you should do a lot of calculations in advance. And you should kind of know like where the moon is before you launch it to the moon. There's a lot of math there. So if you want to do anything that's like applied and in NASA eventually, I do recommend that you go and make sure you get a lot of good math. And MathCounts is a good way to do that, especially if you're a middle school student. Wow, lots and lots of questions. Some person has asked me, what will you do besides math when you retire? So what you've probably been able to figure out by now is that I actually just like thinking about hard things. And therefore, I actually don't want to retire. I think I'll be really bored. I really seriously think that I would be extremely bored if I was retired and there was like nothing hard to think about. So in some sense, my only hope is to be able to hopefully have the health, to be able to continue actively thinking about things, hopefully continue contributing to things for a long time. Because if I couldn't, I'd be really bored. So I wanted to share that with you because some people, especially when you're young, your hope is that, you do some hard work and then you retire and then it's easy. One thing I learned from challenging myself with competitions is that the fun part is the thrill of the hunt. It's not the prize. The prize is just like, it's there. And okay, now what? You stare at the prize? What else are you going to do with that prize? You can't eat it. I guess you do bite a gold medal, right? But you don't really eat it. You don't digest it. But now the deal is, the hunt though, if you've gone through all of the hunt, you just want another hunt. Which is why like you see me doing this now. I'm reliving the fun of the MathCounts, where I'm like, let's go on a live stream where everyone can watch me making all the mistakes. That'll be even more fun because that's the thrill of the hunt. Oh, somebody asked me, will I solve the MathCounts E-Week problems? Well, again, I respect that there are lots of great teachers in this world. I'm not here to run everything. And I encourage you to go and look at other resources too. So my main thing is I came on to go and work on the Math Counts, like official round questions. I'll be doing all those live streams. I'll focus my time on those. Okay, more questions. Oh, Chess and Lattes has asked, what is your advice when you are stuck on a target math counts problem? So if you can see, whenever I'm doing a question, I'm kind of visual. I'll kind of like, even if it's just about numbers, I'll even like lay out my scratch work in rows and columns because I feel that that lets me see patterns. And you see with the Fibonacci thing, I was looking for patterns. My general advice is you probably won't really be stuck. Stuck is a really strong word. It will be that you don't recognize how to do it immediately. That's totally different from stuck, right? Like there's a difference between being like, I don't know how to do this, I've never seen it before, and I literally have no more ideas. Don't feel like you don't have any more ideas. Try to resketch the problem, make the numbers easier. Try to see if you can find some pattern. Try to see if you can maybe see some other part of math that could be useful to solve it. That's what I would do if I was stuck on a question. And I'm stuck on questions a lot, and that's just what I do. All right. Oh, neat. Sabari has just asked, is stars and bars important for math counts? Yes, it is. That's one of these things about, like, if I had to divide up 8 gold coins among 4 pirates, how many ways are there to do that? In fact, it was math counts that taught me that. Actually, I just taught an entire lesson on that this afternoon. So if you like this sort of stuff, you can actually go and check this YouTube channel. There's a video that went out this afternoon around 2:10 p.m. where I was teaching the stars and bars to my college students. Although we basically covered that in like, okay, we covered that formula part in like 2 minutes, and then we spent the remaining time finding out all other really neat things you can do with chooses and Pascal's triangle and like other ways to look at stars and bars. But I do have a lesson on that, and it's free, and it's on this channel earlier today, now that you asked. Okay, we're over time, so let me take just one more question, and I'll finish up. Okay, I'll take 2 questions. The first one I deserve. Leo Gu asked, what is the probability that you will get a haircut? This is awful. I need a haircut. And I was just telling my students the other day, I was telling someone the other day, the way I can figure out when to get a haircut is that it's entirely related to how many of these comments I get on my YouTube saying he needs a haircut. So I need a haircut soon. I'll try to get one soon. But let's do a real question. Yeah, let's do this one. Suguru, what bring you to math? What brought me to math? Well, what brought me to math was the challenge, right? The sheer fact that there are such interesting questions which you can understand the question, but you might not be able to solve. And that search for the unknown is actually very interesting to me. And what brought me to realize this was these math competitions that I played with when I was in middle school. So I'm really glad you guys all came to this live stream, because hopefully you can also see how these are fun. Even if you don't win, doesn't matter. At least go and play with these kinds of things. You'll learn how to think. And maybe you'll start to see like, oh my gosh, math is much more than just a bunch of numbers you multiply together. It's actually neat. There's like all these nifty patterns. And that's what keeps us going. We as human beings love finding nifty patterns, and math is a great source of them. With that, I guess that's going to close out our live stream for the chapter competition. I'll be back because there will be a chapter invitational competition, and that will also be on this particular channel. We will do that in a few weeks. I think the dates of it are probably said somewhere on my website. My website is poshenloh.com/live. That's where we have all of these live streams advertised. I hope the questions won't be too impossible, but I'll try my best anyway. Until then, it's nice to work with all of you, and have a great day. See you then. Bye-bye.